Okay, in this video we're going to talk about kinetic molecular theory. So kinetic molecular theory is a theory that attempts to explain the properties of an ideal gas. Now, it's based on some speculations about some of the behavior of individual gas particles in a mixture or in a container. But for the most part, it explains some of the behavior of gases. But real gases do have some deviations from what we state in the kinetic molecular theory. So we're going to go through some of the postulates of the kinetic molecular theory, and then we're going to talk about some of the ways in which they're accurate and some of the ways in which they're not quite so accurate. So one of the postulates of the kinetic molecular theory is that particles are so small when you compare that with the distance between them, that we can essentially assume that the volume of the gas particles is something we can ignore. It's almost negligible, so we consider it to be zero. Now, there are some conditions in which that's not the case, and we'll talk more in detail about that in just a little bit here. But for the purposes of the gas laws, we generally assume, to make our lives easier, that the volume taken up by the gas particles is so small that we can just ignore it and just consider the size of the container. Another postulate is that particles are in constant motion. So we assume that gas particles are moving all the time throughout their container, which is pretty much the case. And we also assume that the collisions of the particles with the walls of the container are what the gas pressure comes from. So in other words, the gas pressure is caused by particles bouncing off the sides of the container. But the particles are assumed to not exert forces on each other. So it's assumed that particles are attracted to each other, they don't repel each other, they don't interact with each other in any way. And it's also assumed that all of the collisions between particles are elastic, meaning they simply bounce off each other and keep going. So because they don't exert any forces, the motion of gas particles hitting against each other as they move around is not considered to be part of the reason for gas pressure. So gas pressure, according to kinetic molecular theory, is solely due to pressure, the pressure of the gas particles hitting the walls. So the other postulate of the kinetic molecular theory is that the kinetic energy of gas particles is assumed to be directly proportional to their temperature. So as we increase temperature, we increase kinetic energy. If we decrease temperature, we decrease kinetic energy. So we can actually relate the kinetic molecular theory to all of the gas laws, or to most of the gas laws. So let's take a look at some ways that kinetic molecular theory explains some of the gas laws. If we look at Boyle's law, pressure is proportional to 1 over volume. So if we decrease the volume of the container, we increase the number of collisions per unit area of the container. So we know that pressure is force per unit area. So if we increase the number of collisions per unit area of the container, then we increase the pressure. Dalton's law tells us that the partial pressures of each of the gases in a mixture add up to the total pressure. And that kind of goes along with kinetic molecular theory, because the total pressure depends only on the total number of moles of gas, not on what gases we have. Avogadro's law tells us the volume is proportional to the number of moles. Well, if we increase the number of moles of gas in the container, and we want to keep pressure constant, If we're increasing the number of moles, we're going to increase the number of collisions. If we're increasing the number of moles of gas, we're going to increase the number of collisions with the size of the container. So the only way to keep pressure constant is to have a larger volume. Charles's law tells us that volume is proportional to temperature. If we increase the temperature, we increase the kinetic energy, which means if we increase the kinetic energy, particles are going to hit against the side of the container harder and more often. So if we're going to keep a constant pressure, then we've got to increase the volume. Hamilton's law tells us that pressure is proportional to temperature. If we increase temperature, we're again going to increase the force of collisions. If we're keeping volume constant, then pressure is going to increase. So if we increase temperature, we've got to increase either volume or pressure. We can't keep both of them constant. So we mentioned, according to the kinetic molecular theory, Kelvin temperature is proportional to the average kinetic energy. There is an actual equation for that. I show you the equation just so that you're familiar with this. But at this point, I don't expect you to do any math with it. So all the variables mean the same thing they've meant in other equations. Ke with the average subscript here is the average kinetic energy. But all this equation really gets at is the fact that, according to kinetic molecular theory, the average kinetic energy of gas particles is proportional to their temperature. So root mean square velocity is a term that you will see come up sometimes. I don't go a whole lot into the equations simply because they're not really that necessary at this point. All I'm really going to expect you to be familiar with is to know or be familiar with what the definition is. So root mean square velocity refers to the square root of the average of the square of the velocities. So that's a lot of words there. If you take the velocities, and we represent root mean square velocity with this symbol here. If you take the velocities and you square those, and then you average those squared velocities, and then take the square root, that gives you the root mean square velocity. It's used in some calculations. It's also used to explain some of the gas laws. So I give you the definition here. We don't use it too frequently, but there are a few pieces of information coming up that you will need to be familiar with this definition. So there is an equation for the root mean square velocity. They mean exactly the same, the variables mean exactly the same thing they've meant in previous equations, with some slight variations. R in this case is not the same R that you're used to. R is 8.314 joules times Kelvin times mole. M is the mass of a mole of gas particles, but because of the value of R, this needs to be in kilograms. So I'm not going to go a whole lot into the units here. If you think back to or much earlier in the semester, you might remember that the joule is an abbreviation for kilograms times meter squared per second squared. So if you plug all of this in, you have to have mass in kilograms so that the units cancel out properly, so that the units come out to meters per second. So we tend to assume that there are really no forces, no attractive or repulsive forces between gas particles. In real gases, however, there are a large number of collisions. Sometimes, depending on what the gases are, there may actually be reactions, but in the cases where they're not, the path of gas particles is pretty erratic. It's not a nice, neat path the way the kinetic molecular theory would have us believe. The average distances traveled by a particle between collisions in a gas sample is actually pretty small in some cases, depending upon how many particles are in the container and how many collisions there are. There's also a very large range of velocities. We tend to focus on the average velocity, but in reality, not all gases are going to be going the average velocity. We're taking an average of all of the velocities in a sample. So some particles are going so slow they're barely moving. Some are going to be going somewhere around the average. Some are going to be going much faster. And as we increase the temperature, what happens is that range of velocities becomes larger. So if we increase the temperature, for example, we start here at 273 Kelvin. If we go up to 1273, we now have a wider range of velocities. Our range of velocities is nearly doubled here. And if we go up to over 2000 Kelvin, now we're spanning the whole graph somewhere between 0 meters per second and 3000 meters per second. So we've nearly tripled the range of velocities from the original temperature here. So as we increase temperature, we increase the range of velocities. Okay, a couple more gas laws and definitions here that we need to talk about. Effusion and diffusion. And I emphasize the E here just so that it's clear that effusion is different than diffusion. So diffusion describes the mixing of gases. For example, if I have two containers that each have two different gases, so I have my container here with one gas, which is the red particles here, and then I have my second container with a different gas, which is the purple particles here, and then I open a partition between those two containers. Those two gases are going to diffuse into the two containers, and they're going to mix together. So the rate of diffusion is the rate that these gases mix. Effusion is the passage of a gas through a tiny hole in a container. So for example, if I have my container here, which has my gas, which is these purple particles here, and then I have the other side of my container here, which is a vacuum, meaning there are no particles in there. If I poke a tiny pinhole in this partition here, then the gas in this container is going to diffuse through that pinhole, and eventually I'm going to have gas particles on the other side of my container. So the rate of effusion is the speed at which the gas will be transferred into this container here that was originally under vacuum. So the ratio of the rate of diffusion or effusion is proportional to the square root of the ratio of the masses. So if you look at the containers, the equation here, you will notice the rate for gas 1 is on the top of the first side and the mass is on the bottom side. The rate for gas 2 is on the bottom of the first side and on the top of the second side. So the rate of diffusion is inversely proportional to the square root of the ratio of the masses. And I'm missing the word inversely on this slide here. So these two are inversely proportional to each other. So let's take a look at an example here. List the following gases which are at the same temperature in the order of increasing rates of diffusion. So if we calculate the molar masses of each of these gases, which we need to do in order to put them in order, helium has a molar mass of 4.04 grams per mole. O2 has a molar mass of 32 grams per mole. And NO has a molar mass of 30.01 grams per mole. So if we think back to what we've talked about, which of these would diffuse the fastest? Well, they're going to diffuse inversely to their molar mass. So you would expect the lightest gas is going to diffuse the fastest. And then NO and O2 are pretty close in molar mass, but NO is slightly less. And then O2 is going to diffuse the slowest. So helium is the fastest, O2 is the slowest. Okay, so to kind of wrap up the comparison of the kinetic molecular theory to what real gases actually do. So there's a couple of assumptions that the kinetic molecular theory makes that are not really true of real gases. So the first postulate of the kinetic molecular theory is that the volume of the gas is negligible compared to the volume of the container. And the fifth part of the kinetic molecular theory is that gas molecules act independently. These assumptions are true at STP, which is 1 atm and 273 Kelvin, but it's not true at higher pressures. At higher pressure and low volume, meaning we're putting the gas under a lot of pressure in a small space, the volume of the gas is not negligible compared to the volume of the container. Under those conditions, the volume of the gas would actually be taking up a great deal of the volume of the container. And attractive forces between gas molecules are actually pretty significant. There are attractive forces, there are intermolecular forces between gas molecules, so we can't really ignore those under real conditions. There is actually an add-on to the ideal gas law that corrects for real conditions. I don't expect you to do the math with that at this point, but just be aware that the calculations with the ideal gases don't always come out to exactly what happens with real gases. So an ideal gas is kind of really more hypothetical concept. No gas actually follows the gas law exactly. But under certain conditions, under conditions such as low pressure and high temperature, a real gas will get fairly close to ideal behavior. So to show you the deviation between real gases and ideal gases, this is a plot of PV over nRT for several different gases at various pressures. So if all of these gases behaved as ideal gases, the plot should go in a straight line along 1 here. As you can see, they do not go in a straight line along 1. At about 0 pressure, which is really kind of meaningless since we're never really under 0 pressure, they're all right around the line. And there's a point where some of them are on the line here. But once we get to much higher pressures, and down here even at some of the lower pressures, we're nowhere near our ideal behavior. We can do a similar plot at various temperatures, and at lower pressures here we're kind of around the line. But once we get to higher temperatures up here and higher pressures, we find that we're nowhere near ideal behavior for PV equals nRT. Okay, so this wraps up kinetic molecular theory, and we will get some more practice with some of the concepts with diffusion, effusion, and the gas laws in class. So I will see you in class.